the language of the universe.
But I don't understand it.
Hello, everybody. Welcome back to the Math and Physics podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode number 62, where today we have our very first reoccurring guest on the podcast here, Dr. Pekka Sinervo. So for those that remember episode number 4, he was our very first guest on the Math and Physics podcast. So thank you for that. And so we spoke originally about particle physics. He is a particle physicist and was my professor for one of my courses at U of T. That's how we got to know each other. And I think it just continued from there, and we discovered some really crazy things that you have done in your life in that episode. So definitely go check it out.
For sure.
There's going to be a big difference in quality, though, for sure. But before we get into the actual nitty-gritty, let's get into some news on the podcast.
Yes. So now we have reached 123,000 downloads. So
Amazing.
Thank you so much, everybody, for listening to the podcast. And on Spotify, we are now at almost 8,600 followers. And on YouTube, almost 600. So, we're getting close to 10,000 total followers.
That's
If you are listening to the podcast right now, make sure to follow the podcast and leave a comment to possibly be featured for Comment of the Week, right?
Yeah, comment of the week. Also, I do want to mention the 100K Q&A is ready, and it's going to be up on YouTube by this week. So the week that this episode comes out, we should be also just posting the 100K Q&A on the side. So that's going to be cool. So for the comment of the week, we have Aryan Malik. Really nice comment, really long too. I'm going to kind of summarize it. Basically, he starts by saying, how do you not have more viewers? So we love to hear that. He was in a liberal arts program, and there was a lot of rote learning and stuff like that. And I'm just going to summarize the ending. The way you guys talk about math and physics, it made me interested in it again. Keep doing this podcast. I hope you guys get the game you deserve. Enough cringing, back to science. So thank you, Aryan. Thank you for that comment. And yeah, that can kick off the podcast by starting with, we've already got to know a lot about you, Dr. Sinervo. So let's do a little bit for the audience. Let's ask you the best advice that you could give a prospective student in the math and physics program. Just advice that you've received, advice that you would want to maybe, depart to someone else.
I'd say actually go and both talk to your fellow students and get to know your professors.
Okay.
This is, math and physics is seen as a very sort of a technical, mathematically oriented program. It's from that perspective, it comes across as kind of something internal, totally. You just are absorbing stuff and trying to make sense of it. But in fact, the real benefit and virtue of that program is that you actually are with a whole bunch of other folk who actually think and feel the same way you do about math and about physics. And it's really, really important to get to know them and to hear what their stories are.
And one really important thing about just, math or like science in general, I think, is when you study by yourself or just work on anything by yourself, like there's a significant level of difficulty to that. But when you realize that everyone around you is in the same boat, especially like when you find people in that same boat, like, similar interests and stuff like that, as you very well said, talk to like fellows. And I guess you're talking also about like teaching assistants, like anyone that can, assist you with your work can truly open your mind up simply because of the advantage of, communication. Communication in science is a big plus. It definitely helped a lot of scientists.
And in first year, I remember hearing from the upper years, they always say, go to office hours, go to office hours, ask your questions. Even if you don't have any questions, just listen to other people's questions and get to know your professors and people in your program. And I didn't necessarily listen to that advice so much in first year, but I did actually improve like second year. I would go to those online office hours. It was more convenient, but I also realized how important they actually are. And definitely great advice.
Also, we have this forum on, or at least for U of T, and I'm assuming a lot of other universities have it as well. It's called Piazza, where basically, like, I mean, obviously you know it, but for the audience out there, it's basically a forum where where students can, post question answers. Like just an idea like that is so fundamentally awesome for a scientist, because that is how you help each other. Communication and collaboration is the name of the game, especially in a game like this.
It is. And I think the other thing that actually what happens when you get to know your professors is that other opportunities open up. So I'm often asked by second or third year students, how can I get involved in a research project? Mm-hmm. What are the ways that this might actually be possible? And so that opens up a conversation and discussion about what the strategies would be, what are the opportunities that you otherwise would not necessarily have actually uncovered or run into.
Mm-hmm. Mm-hmm. Big part there, yeah.
And yeah, actually a funny thing about Piazza is that in first year, Rayhan and I, we do a lot of our work together, and we actually didn't use Piazza the entire year until the final exam for our calculus class. The final exam was posted, and it's like, oh, any questions you have, go ask on Piazza. So we're like, oh, let's go check it out. And then we see like problem set 1 through 9, like all of these questions being asked and answered, and we're like, how have we not heard of this the entire year? And then we definitely took advantage of that second year.
Right.
Mm-hmm. Yeah, that's a good collaboration. Yeah. It
is, and I follow Piazza when I'm teaching a course pretty actively, because there are questions that come up, and it's a great way of augmenting, office hours and what happens in lectures. You really are able to then elaborate and actually focus on the stuff that students themselves are actually interested in or asking, as opposed to what you think is interesting.
Also on like a forum page or on like a page like Piazza, like again, we're just giving Piazza as an example because we're used to it, but like any kind of forum page like this, you see the advantage of, very specific questions and, trying to really dig deep into some understanding of something. Like in class, not once have I heard any question that like the level of questions that I see on a forum page like Piazza. They're very general questions. Oh, how does this work? Very general but on a page like that where you can collaborate, you go so deep into it that you yourself as the student want to understand so much more. So just that ability to talk to other people that obviously know a lot more than you, like teachers and teaching assistants, like gives you that opportunity, as you very well said, to expand your horizons. Truly does. So maybe we can now get into the actual matter of this podcast and start talking about matter. So and we were talking about this before we started this conversation the recording, but how did we as human beings think about the idea of matter, that things around us are basically matter? These fundamental particles are in these objects. I mean, I'm rambling, but basically, how do we think about it?
Well, so, I think that conversation or that discussion or question has been there for a long, long time. Probably as early as the Homo sapien became actually conscious of sort of the world around them and start asking questions. There is a sort of a change in level of consciousness that occurred probably 50 to 100,000 years ago that moved the species from where it was to where it is today. But the earliest sort of recorded discussions around what matter was really go back to the Greeks. You actually have, in fact, the very first recorded discussion about whether matter might be made of something smaller, particles, that was actually by Democritus. And he and his school that he had actually developed around him, the acolytes, they actually talked about what could actually be the nature of matter. Is it made out of particles? That's actually where the term atom came from. But it was simply a philosophical conversation, in the sense that they didn't really know what that actually really led to. They didn't have a good sense of how large these particles might be, and there was no way of really validating that particular idea. So you have to go fast forward then to now the around the 16th century, when in fact you had now starting to have again what was recorded, sort of more not just discussion now, but actual investigations of the nature of matter, the nature of gases. Thermodynamics developed, what we learned about the way ideal gases work. The pressure times volume equals the amount of material or number of moles times temperature. That those actually all started to develop, and with that then developed this sort of an idea that at a microscopic level, one actually had the idea of particles, which was in fact controversial, and was controversial already even into the 19th century. There were people who actually disagreed with the idea of atoms really being sort of fundamental, and a fundamental description. But by the turn of the 20th century, there were in fact a couple of different, very specific models for what matter might actually be made up of. That atoms existed. That was starting to become a real thing within the people sort of the thinking about how the world worked. But there were still a lot of uncertainty as to what exactly atoms looked like. So it was the experiments by Lord Rutherford back around 1909, which, the famous experiment where he took alpha particles, didn't know what alpha particles were, but they were a form of radiation, plowed them into the gold foil, and watched how they bounced off. And occasionally they bounced off at very high angle, which actually led to the hypothesis that the atom had a very hard core, we now call a nucleus, and then surrounding it, the other particles that eventually were quickly identified as electrons.
Because I always wondered, as you very well just said, I've always wondered how he knew those were alpha particles, because that was the entire experiment. The entire experiment was to see if these things are made up of smaller things. So how could he know that that was an alpha? So technically he didn't, right? That was just what we know now. It's just some form of radiation.
At that point, they had already been able to identify 3 different kinds of radiation.
Okay.
There were alpha radiation, beta radiation, and gamma radiation. They were all forms of radiation that were associated with the decay of radioactive materials. They all seemed to be related to it, and the characterization of what an alpha particle, a beta, and a gamma particle had been done. We knew what the sort of properties they had, but we didn't know what they were. Mm-hmm. We didn't know, for example, that an alpha particle with a helium nucleus. We didn't know that a beta particle with an electron, or that a gamma particle was a photon. In fact, we didn't know they were particles. Okay, we actually knew they were radiation, and radiation at the time was, something radiated. There was something actually moving, and okay, so it was mysterious. It was mysterious.
I never even thought of that. That's pretty crazy.
I wanted to comment on the word atom itself. And I think I read this somewhere, I forget where, but atom means indivisible, right? And so it's this really philosophical question where you have like a piece of wood, for example, and you say, okay, if I cut it in half, and I cut it in half, and again and again and again, when will I get to this point where I have something that is indivisible? You can't cut it in half any further, and that's where the word atom comes from.
Yeah, I mean, but that's not really true now, right?
Yeah.
Now we know that's not right.
No. We actually talk about splitting atoms, right? Yeah. That goes back, right, to the time of the Second World War, when people actually were in the process learning how to actually split atoms, how the uranium, for example, the radioactive form of uranium, could actually split up spontaneously, fission, so to speak. Mm-hmm. But yeah, the idea that it was really indivisible, that does go back, right, to the Greeks.
Yeah.
And in a certain sense, atoms are pretty hard to split. Okay, so you could actually say, well, okay, these actually look kind of the indivisible at some energy level. Mm-hmm. The energy level at which we actually work at or live in, they really are pretty indivisible.
So you also mentioned that there were some people all the way until the 19th century that still did not really believe or take into the fact that, things could be made up of particles or they weren't truly the whole atom. So I guess if they didn't believe that things were, because I guess like you see in like a block of wood, I guess you think, well, what is the smallest thing that you can cut into it? So what is the other ideas that people had? Because I'm
Just
thinking like
continuity.
no, but
Right,
but you have to think that there's something in there, right? Do they just not believe that that's
Yeah.
true?
Well, they didn't necessarily not believe that things were made up of smaller objects, but they didn't actually believe in this idea that, in fact, there were small particles, indivisible particles, that in fact were the fundamental, the underlying structure. There were a number of ideas. There was sort of this plum pudding model where an atom was made up of sort of a jelly or with individual sort of objects inside it. And there were a few other wilder ideas. But just to give you some perspective on it, the chemistry building at University of Toronto
Yeah,
is called Lash Miller.
yeah.
Lash Miller was a chemist who did not believe in the atomic theory.
Wow.
Oh, well, that's
Okay.
interesting.
All right. Okay.
I'll
That
be-
is really interesting, right? Okay.
yeah.
So there's a history there. In fact, there are a lot of stories about how he actually was so opposed to the idea of the atom or the atomic theory that he actually went around, he actually sabotaged people's talks, who were actually giving talking about atoms. Anyway,
Wait, then
piece of
why is
history
our
you can
building
actually
named
go-
after this guy if he's clearly not a good guy? Or is he?
Well, he actually was a pretty good chemist, as it turned
Okay,
out.
so he has made some.
Okay.
Okay, still respectable. Still
I
respectable. in
also
his field.
I find it funny how like when a scientist has his school of thought and there's another group that doesn't think like he does, they always try to convince each other, but sometimes that's just very counterproductive where, one idea may be right, the other may be wrong, but you try to convince the other that your idea is right, but sometimes it's not, and you're just delaying the progression of science.
But I think a lot of the time, sorry to cut you off, but I think a lot of the time, is just collaboration. It's not really like convincing. It's just I'm trying to put my perspective of this argument. You put your perspective of this argument, and let's see which one makes more sense.
Yeah, but I guess I'm trying to say like the thing that's the negative part is closed-mindedness, right? You're not willing
Yeah.
to accept other
People shouldn't.
perspectives.
Yeah, exactly. I guess that property of Lash Miller is not not to be redeemed.
Yeah, but there's actually a lot of philosophy of science here that comes into play. So there's this whole idea of scientific revolutions that was actually made popular in the 1960s. A couple of key philosophers, really, or historians of science, who actually put forward the idea that, in fact, you had revolutions in science. That revolutions were the place where, in fact, you had a bunch of observations that come together and no longer were consistent with what we actually understood or the prevailing theory. And those facts, those observations, ultimately actually put the original theory into crisis. Where, in fact, people now began to realize that they didn't understand something. And maybe they needed to modify the theory, or maybe they just needed to throw it out wholesale. And this idea of scientific revolution, actually you ended up having to have a process by which then a new theory evolved or a new model evolved, and the question of how that happened was in fact exactly the process you just described, where people actually argued with others about what was right or what was more right in terms of understanding things. And the term that was used was that a new theory, evolved and became the thing. When you had a group of ardent adherents, that's the term that was used. People who just believed that what they had now was a model that was better than whatever had been before, and they argued and they brought more facts together, and the new theory had to predict stuff that the old one didn't. And you could go out and you can test that new theory. And if the test succeeded, you increased the confidence that, in fact, this new model was better. But these ardent adherents were the ones who actually made the case. And those are the people who argued the most strongly for something new.
Mm-hmm.
And they're the ones who then led the revolution in some sense.
Yeah, because and continuing on this point, we have in episode 61, we just recorded it. We were talking about Albert Einstein and Niels Bohr and their relationship,
the quantum
and stuff.
revolution.
The quantum revolution, and and a very big part of that discussion, that relationship between Einstein and Bohr, was communication. In the Slovak conference, with their repeated arguments against one another, we wouldn't have, or maybe not wouldn't, but quantum theory wouldn't be what it is today without those arguments, without Einstein questioning how quantum mechanics can make. Because to be honest, I don't think anyone can really think of questions like Albert Einstein can. So if he can ask a question and he's wrong, and Niels Bohr gives an answer, that means we have a very good reason to believe quantum mechanics. Or at least a reason to understand it. So that communication is, again, what that allows, right? Just that, a big part of it.
It is a tension that takes place.
Mm-hmm.
And eventually the tension causes something to break.
Yeah, exactly.
Because one of the things about physics and mathematics and a few other of these sort of subjects is that they've actually developed a practice of looking for the best model. And it's the best model that wins out. The other models, they get put into the trash can, and people forget about them. Now, that's somewhat unique to physical science. Because if you go to the social sciences, for example, or the humanities, you actually find that people work simultaneously with different theoretical ideas. You actually have people who will, in a paper, they'll say, well, let's theorize around these observations. And let's look at it from this perspective. Let's look at it from that perspective. They don't actually argue that one of those two perspectives is better than the other, but rather those are in some sense, truths. Both of them are true, or all of the theory they're actually looking at are true at some level. Physicists don't like to work that way. Mm-hmm. They just don't. They think that there should be one. The one that they should actually be following at any one time.
Very unique physicist for sure.
Yeah, and theories at the end of the day are just approximations for what really is. And so if one approximation is better than the other, then we'll tend to flock to the better one because it it does our job is to describe it better. And so if we can get closer to the truth, then that's where we go, right? We don't tend to stick around the worse versions, I guess.
Mm-hmm. Mm-hmm.
Yeah. Well, and there is something actually pretty fundamental also about that practice, because what it does do is that for a theory to actually be successful, not only does it have to be able to describe everything you currently know, but it has to be predictive. It has to be able to actually put forward prediction that you can then test. Theories that don't do that are dead theories, right? Because they don't actually allow you to go further. And that's one of the sort of fundamentals of, physical science, where, the theoretical ideas are what push forward your understanding and then prompt you to ask particular types of questions, which then allow you to further develop and understand what's going on until you come to a crisis where all of a sudden the theory no longer is able to describe what you're actually observing. And now you realize, this approximation, I've come to the boundary of where it's valid. And now I actually have to go to this other theory or this another model, right? That Parker, you actually talked about.
Yeah. Yeah.
Yeah, and one of my favorite things about general relativity is actually the fact that it predicted that black holes existed, and only recently in my lifetime they were actually confirmed with hard proof. It's here's the picture of the black hole, and then Einstein's not around to see it, but it's such a great realization of how amazing the theory really is.
Yeah, theories can be powerful, man. Very powerful, truly. And we're seeing it. And I think now I can ask, because we've been, discussing about matter and theories of matter now, how did the whole antimatter argument come into play? Like, how did I mean, even though it's quite an interesting topic to talk about, and we will obviously, but how did we even think about there being an anti whatever we see? Like, how was that process? What was that process?
So that process actually developed in the late 1920s, early 1930s. And in fact, the theoretical idea came forward first, and then the observations that the antimatter existed. So you have to go back to Dirac, Paul Dirac, was this this great mathematical physicist. And he was trying to develop a quantum theory that was consistent with special relativity. Okay, special relativity was agreed that it actually was real. Been around now for several decades. Quantum mechanics was only starting to develop, right? This is 1928, 1929. But Dirac actually started working on this idea of, well, how can you have a quantum theory that actually also agrees with special relativity, that incorporates special relativity? So he worked very hard on coming up with a set of equations, which are basically extensions of the Schrodinger equation, as we now know today. Or alternatively, the equation he developed, the Dirac equation, the Schrodinger equation is an approximation to it in the sort of non-relativistic realm.
Well, I did not know that. Okay.
So what he discovered when he actually put together the mathematics was that, in fact, his theory predicted not only positive energy states, but negative energy states. And that was actually a real puzzle. And in fact, it was seen as a failure of his theory, because what is a negative energy state? It doesn't make any sense. But he then proposed that, well, maybe there's some ghost particles that are associated with those negative energy states. And in fact, what he realized was that if he actually thought of them as opposite in charge and opposite in all the quantum properties, you could actually think of them as actually real states, real energy states of a particle that was opposite to the ordinary particles. That was the idea. This was like in the early 30s. It was about a year and a half later that people actually observed an anti-electron. And this was, they did that because it actually comes out in a radioactive decay. You actually get a particle, which is in fact not negatively charged, but positively charged with the same mass of an electron. So the discovery of the positron took place after the theoretical idea came up, and that was then, there had been this prediction by Dirac. The anti-electron or positron was discovered, and people then believed. Right? People actually realized that the Dirac theory was in fact had to have some validity to it, and people started calculating with it, and they saw that it was very successful in predicting phenomena. And that's exactly the theory or the equation that we use for all of our calculations in particle physics nowadays. It really starts from the Dirac equation as opposed to the Schrodinger equation. So that's how we actually learned about antimatter first, and then eventually we actually discovered antiprotons. But that took actually quite a bit longer because you had to create them. They were not generated naturally in the nature. And you can understand that to a certain extent because there wasn't a radioactive process that created antiprotons. There was one that created anti-electrons. So you had to find a way of putting enough energy together to create an antiproton, for nature to create it by having enough energy density.
And were they able to do this in like particle accelerators, or was it before that?
It was with particle accelerators.
So particle accelerators is what is when we saw our first antiproton.
Right.
Basically.
Correct.
Okay. Wow. The antiproton. That'd be so cool.
Yeah.
And Parker has, and I want Parker to say it, but because we were talking about it the other day. He has
I was
really
about
cool
to ask.
theory that I want you to listen to, and I just want to hear what you think about.
Actually, I
Or
think we're
it's a
thinking
famous
about
theory.
different things, but anyways. Okay, so I was reading QED by
Yeah,
Richard
okay, that's fine,
Feynman,
yeah.
where he talks about, the Feynman diagram and all that. And so it's like you have space and time on the two axes, and you can describe like an interaction where you have an electron positron pair annihilating into some other, like a photon or something like that. Yeah.
Photon.
Okay, but I don't know if I like understand exactly what is meant to happen here, but there was an arrow, right? An arrow in the electron pointing towards the annihilation, and then the arrow for the positron was pointing away. And so in my head, I was thinking that the positron is the electron going back in time, because you go along the time axis, but the arrow's pointing in the other direction. But I don't know. That was just what I was thinking.
Well, in fact, it's convention that you actually think of you actually put in a Feynman diagram, you put all the antiparticles going in the opposite direction to the way that they would go if they were the normal particle.
Mm-hmm.
And it actually is very nice to see because, in fact, when you have that kind of a decay vertex, what really is going on is that you have a particle coming in, you have an antiparticle coming in, they annihilate, and so you have a photon. But if you look at it a different way, you have an electron coming in, and you have now the positron going out. Now, if you turn that diagram,
yeah, it looks
by
like an
90
emission,
degrees,
right? Yeah.
right, then you actually have an electron coming in, is emitting a photon and continuing.
Right, because of the change of momentum of
Yes,
by emitting
exactly.
a photon. Yeah, that's
Exactly.
what was so interesting about it, is that in one way it's a pair annihilating, and in another way it's an emission with a change of momentum, which is
Correct.
so
Correct.
cool.
And both of those are described by exactly the same phenomenon, the same strengths of interaction.
Yeah.
So the Feynman diagram allows us to, in a very systematic way, identify the interactions, because each of those vertices, the place where the electron and positron come together and annihilate, we call that a vertex, and there is a strength to that vertex. And that's actually predicted by the strength is actually an element of the Dirac theory. And so you can actually go and measure that process and actually know what the coupling is. That's the coupling at the vertex. And there are a set of rules for how you actually calculate. Once you know the coupling, a set of rules for how you actually calculate the actual quantum amplitude associated with that. And it miraculously or not, but it all works out exactly the way that you expect. And this is actually one of perhaps the most tested physical theory we've ever had. We're testing it to the level of over 9 decimal places.
Wow.
Making predictions
Yeah, that's incredible.
with that degree of accuracy, and we're able to measure things with that degree of accuracy, and it works. Right?
Wow. So we don't have positrons moving backwards in time.
Well, we don't in that sense. We have them moving forward, but it's equivalent to an electron moving backward in time. That's the point. It's equivalent to an electron moving backward in time.
I read this.
I don't know if this is I don't know if this is related in any way, but this reminds me of like having a current of electrons going one way is the same as having like positive particles moving in the other direction when you're talking about electrodynamics.
Yeah. It has some analogies to it, but the relationship between matter and antimatter is in fact quite specific. Whereas some of the other things that you actually have, for example, electrons moving in one direction, and you could actually think of a current going in another, those are in fact properties of charges that are flowing or that are moving. And they're not really about the fundamental nature of matter and the existence of antimatter. So when it's important to keep these things separate and in their own compartments in a certain sense, because they really are driven by a completely different physical phenomenon.
Right. I was just reminded of that idea of like moving backwards is the opposite of the other moving forward. But yeah.
Also because it's like kind of convention that we have electrons moving one way and current moving the other, and saying that current is positive.
That's it.
Technically, it's just, I think a lot of it is just convention, because
Yeah.
that's just how it is. Like, you know, those memes or those jokes where like if electrons and current move in the same direction and we have like a futuristic world, like, you know, like jokes like that. Like, it's just I think a lot of it is just convention. And I mean, now that we're talking so much about antimatter, I have to ask, and obviously no one knows, but what's the deal with baryon asymmetry? Basically, the theory that matter and antimatter aren't, or not theory, but the fact that they aren't equal in the universe. Like, is there anything now that we know that maybe would, like, you know, enlighten that question for us, like a little bit?
Yeah. So there is in fact one very standard theory now that would explain why we actually have this asymmetry. And this actually goes back to the early universe, and what we call inflation. Right? Yeah. There is this model where very, very early on, the universe was very, very tiny. It was in a very specific quantum state, and then all of a sudden there was a phase change. And that in that phase change, there was a non-equilibrium process where all of a sudden the universe grew very, very rapidly in this sort of non-equilibrium state. And there were interactions between the particles that were not that had an asymmetry in them, where charge parity wasn't conserved, as a symmetry, and that combination of a very rapid change, non-equilibrium, plus having this charge parity asymmetry, would lead you to the prediction that in fact you would actually have a change from equal numbers of matter and antimatter particles to a large asymmetry.
Mm-hmm. Sorry, but maybe you just want to briefly explain like charge parity, because we've heard and spoken about parity symmetry a lot, but never actually had an explanation. So maybe you want to do like just a quick, brief thing before you get back on track on charge parity symmetry and why this asymmetry is a big deal.
Yeah. So charge symmetry means that, you know, a positive charge will always remain a positive charge, and we actually have seen that. We don't have any evidence that charge they're the failure of the symmetry of charge. The charge seems to be really preserved. Parity is in fact for every particle they have a very specific parity, either positive or negative parity. And you can think of it as actually whether in fact it's the left or right-handed in terms of its behavior.
Okay.
And parity itself appears to be preserved, but the product of charge and parity isn't conserved. In fact, there are some processes in nature where, in fact, this charge parity is violated maximally. In other words, that one process can't happen, but the other can. And this was actually discovered back in the late 1950s. Won a Nobel Prize, because it was something that was just completely not anticipated. But charge parity is not a true symmetry of nature. And so we actually see this, what we call CP violation effects, take place in a lot of different systems. And the one that in fact we see it most very clearly was in the interaction of neutrinos and charged leptons. There you actually see that in fact everything has to be left-handed. Everything has to be left-handed. So it just means that there is no right-handed interaction that can take place. So that's actually the violation of charge, the CP violation, maximally as we talk about it. But there are other particles like quarks, like the bottom quark, that appears that doesn't actually conserve CP, the charge parity. The discovery of that, and that bottom quarks can turn into anti-bottom quarks. That's basically what CP violation really means. You end up then being able to use that as a way of predicting that in fact you had could have this asymmetry in the early universe that with inflation would actually result in this baryon asymmetry. And you only needed a small change, because if you think about it, when the universe cools, if you have a small change in the small asymmetry between baryons and antibaryons, the baryons and antibaryons essentially annihilate each other and turn into photons. But if you have an asymmetry, you're just left with then a small excess of baryons. And that's exactly what we see. The universe is filled with photons, and there's a very small amount of baryons that make up ordinary matter, the protons and neutrons. That's what our universe is like. It's basically, most of it, almost all of it, is just photons.
So, wow. So we actually almost do have a theory for understanding baryon asymmetry.
We do, except...
So is this a theory, or is this like basically this is what happened?
No, it's still a theory.
Yeah, it's still a theory, right? Okay.
First, we weren't there. Okay, so let's actually be clear. We weren't there at the point of the immediate after the Big Bang.
Of course,
right?
We don't know.
Good. We don't know. But actually, more importantly, we don't know that there isn't actually a particular process, CP violating process, that's strong enough to actually give us the amount of CP violation we need to make the big inflationary model work. We have evidence that there are processes that do violate CP, the charge parity, but having one that's strong enough is still an open question. Now, with the discovery that neutrinos have mass, that opens up the possibility that, in fact, all of this asymmetry took place not in the baryon sector around quarks, but with the lepton sector. Between leptons and between the charged and neutral leptons. So that's an idea. It's another theoretical framing of it that could actually get around the fact that among the quarks we don't seem to have enough CP violation to actually explain what took place in the early universe. But a lot of the data is so consistent with this model that it's hard to get away from it. No one has come up with a better model for describing. So that's why we're stuck with it for the moment. But there are these questions. And by the way, it doesn't explain dark matter.
Yeah, that's the whole new
great
whole new model. Whole new model for sure.
And I had a quick question. So we're talking about quarks, and I was wondering if humans started really talking about quarks after they started playing with particle accelerators, or were they theorized before and then confirmed afterwards?
So particle accelerators were already invented back in the 1930s. You have to go back to Lorentz, who was actually building the first cyclotron. And those first cyclotrons were very small. They were kind of, they could hold one in your hand. But he actually demonstrated that you can actually accelerate particles in this little, very well-machined copper device that was given the name cyclotron. And so he then went off and started building bigger and bigger ones, along with other people, but he was the one who was sort of in the lead. And it was all happening at Berkeley. And so now we have the Berkeley Lab, or Lawrence Berkeley National Lab, that is in fact the place where the cyclotron really was developed. So by the time we got to the 1950s, we actually had energetic enough cyclotrons that you could actually now start producing other types of particles that we hadn't observed before. And so there were these strange particles that decayed. And they decayed in funny ways. So they were actually called strange particles. K mesons were the first one that were discovered. And there were funny properties to them. So you had, at that point, protons and neutrons that looked almost identical, right? Almost the same mass. One was charged, one was neutral. They actually all were found in the nucleus. So that was one puzzle. The other puzzle was these strange particles that were produced. And at the same time, one was able to produce other forms of particles like the baryons, like the proton and neutron, but that were heavier and decayed. Okay, so that was a picture that we had in the late 1950s. And so a number of theorists were trying to figure what could explain all this. And that's when the quark model was developed in the early 1960s. It was two people, actually, who were sort of working somewhat independently, Zweig and Jeanman, who actually developed this idea of a quark model. And Gell-Mann and Zweig showed that, in fact, it would describe most of these things. Didn't actually give everything together, but it gave a way of actually predicting which particles you could find. And that was actually the beginning, where, in fact, these ideas of quarks emerged. And you needed three types of quarks, an up quark, a down quark, and a strange quark. And you could explain at that point everything that we had seen so far.
Wow. That's what we needed. That's what we needed.
And back in the day, when they were just seeing like, oh, we have these heavier protons and lighter protons that decay and all that stuff, we're talking about very, very small masses. So how are you actually able to distinguish between small and very very, very small?
So at that point, we'd had no idea what the masses of quarks were. We knew what the masses of protons and neutrons were. We knew what the masses of electrons were. Electrons seemed to be about 2,000 times lighter than protons. But we had another particle which was a cousin to the electron, a muon. And the muon was, approximately 250 times heavier than an electron. So kind of midway between protons and electrons. So the challenge at that time was to actually understand, when you talk about quarks, how would they be able to predict or explain the masses of the particles you did observe? And there was no easy way of doing that, because if you actually took, the proton and neutron, we thought were made up of three different quarks. So that would suggest that a quark had a mass of maybe a third of a proton or neutron. But then you had particles called pions, which are only about 15% of the weight of a proton and neutron, and seem to be made up of a quark and an antiquark. Well, so how did that work?
I was just going to ask you a question on mesons, because it's the concept of a quark and an antiquark in a like wrapped up in a particle. So, which I was wondering, how can that exist?
Right. So so it's a bit like an atom itself had electrons surrounding a nucleus, and so the electrons are bound to the nucleus. If you think of the nucleus, the neutrons are bound together. And we actually talk about the nucleus as being bound together by the strong force. The nucleon, the proton, the neutrons being held together by the strong force, and the electron is held bound to the nucleus by the electromagnetic force. So this idea of the strong force was then extended to actually to be used to actually describe how quarks and antiquarks bound together. Now, if you were to the solution to this puzzle of what the mass of quarks was the recognition that, in fact, the mass of a particle was not simply given by the mass of the constituents, but by the energy that was actually associated with the interaction of the quarks and antiquarks inside the object. And that determined the mass of the particles, not the masses of the constituents.
Because a big realization, I believe, was, especially after special relativity and everything, they found out, or not found out, but I guess they calculated that most of the mass of anything does not actually come from these quarks, but it's the strong nuclear force. It's the energy that's holding these quarks together, where most of the mass of the particles are coming from, which was kind of surprising.
Yeah.
Right.
Yeah.
And
exactly.
So we've spoken about matter and understanding matter, antimatter. We've spoken about the fermions, the leptons, understanding particles. One thing we haven't got into, even though we have alluded to it, are force-carrying particles, or bosons. So bosons are also a very important part of the standard model, what we call force-carrying particles. And the ones we know now, we have the strong nuclear force, the weak nuclear force, the electromagnetic, and the gravitational, right? The strong is, and they're all carried by different particles. So maybe we want to get a little bit into how did we think about again, particles, I guess, now that we've already got through that explanation, we can think about an object and, well, what's smaller than that? But when we think about these force-carrying particles, what's our logic there? How do we get to that?
Well, so this comes back to really the fundamentals of quantum mechanics and the prediction that had been developed through the development of quantum electrodynamics, that the carrier of the electromagnetic force could be understood as a photon. Okay, so that in fact was the first boson, spin 1 particle. By the way, it doesn't have to be spin 1, it just has to be an integer spin. Spin 0, spin 1, spin 2, so on. So a photon at spin 1, and when you actually calculated using the Dirac equation the behavior of the electromagnetic force, you found that in fact it described exactly the behavior of electromagnetism. That's why we call it quantum electrodynamics. Taking into account special relativity, you can describe all of the behavior of electromagnetism by introducing this idea that there was a force carrier, a photon, with very specific properties. The photon connects particles with charge, does not actually interact with neutral particles. So you needed an electric charge around to be able to have photons interacting.
When you say carrying force, like force carrying particles, like I'm just trying to apply intuition.
Okay.
I guess I'm not really deeply thinking into it. Like, what does that really mean?
Well, so it's not really carrying a force.
Yeah, okay.
What it is its behavior actually is responsible for what we call the force.
Oh,
we actually talk
okay.
about force as being Newton's laws, F equals ma.
Mm-hmm.
Well, actually, force is a theoretical concept. We don't see force, right? We don't see a thing called F. What we actually see are the acceleration of particles, right? That's all we see. That's all we see. We only see acceleration. So we infer from that there's a force. That wasn't Newton's idea, or an idea of several others, but Newton was the one who put it into a nice framework of 3 laws. But the idea is that you can actually explain the acceleration of particles by introducing this idea of force. Okay.
Mm-hmm.
Now, but it's purely a theoretical idea. You don't see a force. You don't see a force field. You just see the acceleration of particles. Okay. So when we actually then get to now quantum electrodynamics, what you're actually seeing are the interaction of charged particles, and they accelerate. They either attract each other if they're opposite in charge, or they repel each other. And what we're actually really saying when we talk about photons as carrying the force, it's actually the exchange of photons between these 2 charged particles that actually results in a net force. We actually already talked about the fact that if you took that annihilation diagram of electron, positron, and a photon, you turned it 90 degrees, you now had an electron emitting a photon, and actually its momentum being the change because of momentum conservation. Well, that particular picture, you have to now think of it happening almost an infinite number of times. There's not just one photon, but it's a bunch of photons.
Mm-hmm.
And they're interacting. And when you actually calculate the net effect of all that, you find that, in fact, you get for charged particles that are opposite in charge, you get an interaction which is repulsive. And for particles that are opposite in electric charge, you have an interaction that's in fact attractive. And that's actually how we think about. That's why the idea that we talk about photons as, quote, carrying the electromagnetic force, but it's really the interaction of photons with the charge-carrying force of charged particles that actually result in their acceleration, and what we now call the electromagnetic force.
Wow.
Wow. That was a whole new definition of force. Wow.
Yeah. And so when we talk about the strong force, we're actually also talking about the fact that protons and neutrons are accelerated toward each other. And that's what we actually then infer as the strong force. And so when you actually think about the strong force carriers, which we call gluons, they have to have special properties that they can actually keep protons and neutrons bound together. If you had two protons close to each other, even though they're positively charged and the electromagnetic force will want to push them away, the strong force is stronger and pulls them together, causes them to accelerate toward each other. But one of the properties of the strong force is that if you get far enough away, it vanishes much more rapidly than the electromagnetic force. So it's what we actually recognize as not being a long-range force. It's in fact a short-range force, and only acts in the sort of the distance scale of what we see of an atom, the atomic nucleus. Sorry, about
And sorry,
Yeah.
are the gluons in this case the force carrying particles for the strong nuclear force?
Yes.
Okay.
Right. And there are 8 of them.
Oh wow.
There are now 8 of them. And those 8 are needed to be able to explain all of these funny features of the strong force. Where the electromagnetic force, we only needed one, one photon, but we have 8 different kinds of gluons that actually are needed to describe the strong force.
So what's an example of like a funny feature that we need different types of gluons to explain?
Well, so the one I already mentioned, the fact that the gluon, if you only had one gluon, then the force would actually, by virtue of the interaction, would be long range. And we know the strong force is not. So we have to build it up so that, in fact, over a particular range, that force can be very strong. And then it actually dissipates. It drops off. The other factor is that when we actually have particles that are very close to each other, that force drops off. So you have this property that, in fact, we have what we call asymptotic freedom, where if the quarks, for example, get close enough together, then they don't feel a force. They're sort of free, and they're in like a bag, where the size of the bag is determined by when the strong force turns on. And inside the bag, they're actually just freely moving. Now, this factor of the fact that the strong force then disappears when you get out to very large distances is because it only acts on particles that we say have the quantum number called color. So when you get far enough away, the object that the photons or the gluons would see becomes colorless. Like all of the quarks actually are such that their color balances out, so they have 0 color. So a proton has 0 color, and a neutron has 0 color. But the constituents inside don't. They are colored. And that's why when protons and neutrons get close enough together, they actually attract each other. Because of the fact that the strong force actually sees the colored objects inside the proton and neutron.
I love the idea of colored particles. Yeah.
So that's why you needed that's why you need this plethora of force carriers to be able to describe all of the features of the strong force.
Now here for the big one, what about gravity though? What is your opinion on gravity? Is it part of the standard model, i.e. is it carried by one of these particles like a graviton, the hypothetical graviton? Or do you believe, similar to Albert Einstein, its fundamental nature of space-time? Like, what is your take on gravity? Should it have a place in the standard model?
Well, just to be clear, it's not part of the standard model.
Not yet. No, of course. No, not right now. That's the question.
And the graviton is, in that sense, a hypothetical particle. Totally hypothetical. We actually have no evidence
whatsoever
that the graviton exists.
Just an idea.
Just an idea. We know that gravity radiates, right? We have radio wave, gravity waves, and it wasn't simply because we found that we've observed the merger of black holes using very sensitive gravity wave detectors like LIGO and Virgo. But we actually saw pulsars, where you had 2 binary stars rotating around each other and causing a radio beacon. We actually saw the decay of pulsars. And Taylor and Hulse were the first to observe that. And the only way you could understand the change in the rotation rate of this binary system, was if they were emitting gravity waves.
Mm-hmm.
And so that was really the discovery. That goes back to 1967, 1968. Sorry, early 70s, I think, actually.
Mm-hmm.
But anyway, so the point being, though, that we actually saw gravity waves a long time ago. But gravity waves don't tell us that we have gravitons. They aren't evidence that
because they're not really
exist.
radiation, right? Like, it's not really radiating anything through space. It's space itself that's moving, right?
Well,
Isn't that the
again,
whole thing?
But that's actually the geometric way of describing the effects of gravity, which, there is nothing that tells us that, in fact, everything has to be a quantum field theory in our world.
I guess that's
There's
true. So we don't have to
nothing
quantize everything, basically.
We don't have to quantize everything, especially something which is like space-time. It's not a particle. We're not seeing accelerations of particles as a function of space-time. I guess we are a little bit in the sense that we actually talk about the force of gravity. But in fact, it's the curvature of space-time which is actually causing it. It's the distortion of space-time. So I'm not convinced that you actually will find that there is, in fact, a quantum theory of gravity. Okay, now that may be for some people that may be heretical.
Yeah.
But however, the smartest minds have actually been trying to pursue this idea because everything else is successfully described by quantum field theory.
Interestingly enough, I'm doing a research program this summer, which is trying to prove the quantum theory of gravity. It's basically, it's kind of doing, it's in that regime. So it's really funny that you mentioned this, because I'm just thinking, because I mean, it's a nice idea. I guess the idea is there, but I guess as of right now, there's no real implementation. There's nothing really that we can say yes or no to. Like, there's a lot more no than we can say yes.
Yeah, there are ideas. String theory has been one of the ones that have been most popular for the last 30 years as a possible description, right, of gravity in a context where it's quantum field theory, and you can actually do calculations with it. However, it has not yet yielded a particular prediction that actually we can go and test. You can come up with theories that look a lot like what we see around us, but they don't then predict a bunch of things that we can actually go and observe, not at a fundamental level. You have to then add something on top of them to be able to get predictions, and that's a fundamental problem. And there are people who are working on that problem, and some people think they solved it, but I'm still skeptical. I'm skeptical. I'm skeptical still. Yeah. Okay. Yeah. But I'm just a dumb theorist. Or a dumb experimentalist.
We're excited. We're excited.
Yeah, I can't wait to see what happens. But I wanted to ask you about supersymmetry. And maybe for our audience out there, you can give kind of like a brief explanation of supersymmetry.
A theory, very much so.
Mm-hmm. Mm-hmm.
Yeah. So it's an idea that was really developed in I think its development really started in the 1970s, in fact, but it really took off in the 1980s. And the reason that it was, so what it is, it's a theory that basically postulates that for every type of particle we have in the quote standard model, all the quarks and leptons, all the bosons, things that we actually talk about caring for, there is a supersymmetric version of each of those types of particles. So for an electron, there's a supersymmetric electron. And most of the time we'll actually talk about them as we just add S to the name. So a supersymmetric electron is a selectron. The supersymmetric quark is a squark. The supersymmetric lepton
scientific nomenclature is so funny sometimes.
Okay, so it's a slepton.
Yeah.
And the force carriers, we actually add eno to the end. So a supersymmetric photon is a photino. A supersymmetric W boson, we haven't talked about weak force, but it's carried by the W and Z boson, is a weno. WINO.
That's
A
ridiculous.
supersymmetric Z boson is a ZINO, ZINO. So you have this whole family. You've doubled all of the types of particles that describe the world. Okay, so whole point. Why do we do this?
Exactly.
Right? Well, we actually do this because it then allows us to explain why, when we actually go to very, very high energies, the theory that we have doesn't blow up, but rather what it does do is it actually causes all of the forces we talk about, the electromagnetic force, the strong force, and the weak force, to come together and look like a single force. And it's that ability of the supersymmetric theory to predict what happens with a standard model. They go to very high energies that in fact makes it attractive, because it without the supersymmetry, you actually have problems with the current standard model. When you go to the very high energy, you have a bunch of sort of problems. Probably the most famous one's known as the hierarchy problem, or fine tuning problem. But the point is that you have these problems. The standard model isn't complete, in other words. And supersymmetry is a way of completing it so that it actually makes sense as you go to higher energies. Okay, so that's the idea of supersymmetry. And there were predictions made that you should observe supersymmetric particles, you should be able to create them and observe them at high enough energy colliders. We didn't know what the mass of those supersymmetric particles were, but it kind of made sense that they should have masses which are sort of the scale that we work at, GeV or tens of GeV or maybe hundreds of GeV. So the problem has been we have no evidence of observing supersymmetric particles. Nada, none. We've actually been looking for them for over 30 years. We have zero evidence
that is an issue.
Supersymmetry is a real model. It is an issue. I've never been a particular fan of supersymmetry. And for the fundamental reason that what it requires us to do is double the number of particles that are needed to describe the world. That's, I subscribe to Occam's razor. And Occam's razor basically says, if you have two theories, one which is more complicated than the other, pick the simpler one. The simpler one is more likely to be right. And so now this is not quite fair to supersymmetry because there isn't a simpler theory that describes everything.
True.
But you have to accept a lot of extra baggage by taking on supersymmetry in order to get the right answer. And that just seems like a pretty costly load to assume.
So are there other theories for this high energy spectrum of the standard model?
So there are other ideas that floating around.
Popular as supersymmetry or no?
No, they haven't. Really. And there have been various problems with them. One of them was called Technicolor. Okay. That came out in the 1980s.
Sounds cool.
And it was another way of describing what took place at high energies. Turns out that most versions of Technicolor have actually been shown to not be consistent with the data we currently have. And there are a whole bunch of versions. There's walking Technicolor, in event. There's just a different ways of thinking about it, and none of them have actually worked out. Okay. So people are still working at trying to find alternate solutions, especially since we haven't observed any evidence for supersymmetry.
That's a big problem.
Makes sense.
As Parker said, it's a big problem. You predict something and you've been able to wiggle out of it only because you don't know. You don't have a firm prediction as to what the mass of the supersymmetric particles could be. Maybe they're, several TeV in mass, and we just haven't built the energetic enough collider to be able to produce them.
Right.
So talking about the energetic enough colliders, and we were also saying, we haven't found them so far. I just really wanted to ask, what do you, obviously having worked at CERN, for those people that haven't got or listened to episode 4, who've worked at CERN, what do you think will be, or what do you think we can do to build or to amplify the future of particle accelerators? Like, what would the future of particle accelerators look like? Best case scenario.
Yeah. Well, let me just make the point that particle physics is not simply about building accelerators.
Of course,
Or
but it
building-
does allow us to, gleam into a lot more of reality than
Yeah.
we can with the current world around us, right?
Correct.
Yeah.
Yeah. So, yeah, so the future of particle accelerators is a little bit unclear. There are ideas for building more energetic ones than what we currently have. Heck, we were going to build a very energetic one, a 40 TeV collider, back in the 1980s and early 90s, called the Superconducting Super Collider, and being built in Texas until 1993. And we had to settle for the LHC, the Large Hadron Collider, which was only designed to go up to 14 TeV. For very practical reasons, we were reusing an existing tunnel, and the size of the tunnel dictated the energy of the protons that we could put in. So the next stage is to actually build accelerators that use a different technology and accelerate different particles. So, for example, one of the ideas is to build a muon collider and an electron collider, electron-positron collider. Now, the muon collider has the potential for going up to much higher energies. And that's simply because the muon is heavier than the electron, and that means you can accelerate it more easily. There are other ideas for building a much more energetic proton-proton collider. That's about 7 times the energy of the LHC. So there are these ideas, and people are pursuing them, and we're trying to figure out how much it would cost. So that, what we call the energy frontier, is sort of pushing along. But it takes generations. If I were to actually go back to I've been in the field for doing experiments for 40 years. Now, 40 years ago, if I were to ask the question, what was happening? The high energy frontier was being given at Fermilab, where they were building what they called the Tevatron, a collider that would collide proton and antiproton together at 2 TeV. And that was just being constructed when I got into the field back in the late 1970s. Started doing the first experiments there in 1986. I was on that first experiment that actually started using the Tevatron, the collider. And we worked on that experiment for 25 years, constantly upgrading the luminosity of the collider, and actually looking at more the rarer processes. It's how we discovered the top quark, for example.
The only future of particle accelerators is just increasing the energy, basically. Like there's nothing,
and the intensity.
So there's no like fundamental difference that we can think, like, instead of I don't know, I guess there's no, I'm just thinking I guess accelerating it in a circle probably is the most efficient way to do it. But I'm thinking like, so there's no fundamental difference. It's just intensity and energy increasing, and we'll simply be able to, see more of the universe. Okay.
I think we need to see. Sorry, I was just going to say, I think we need to see an accelerator that goes around the equator of the Earth.
Yeah. No, and people have actually thrown out the idea of, why don't we build an accelerator in the outer space? It would be huge. It would actually allow us to actually
very expensive
accelerate particles.
Would it not? Because to lift it up there would be crazy.
It would be.
Even if they do it in parts, that would be so expensive. Yeah,
right.
For sure.
So people have been thinking about it, but it is a challenge. So but this is ultimately how particle accelerators have developed. People have actually been creative and imaginative. They've sort of thought about how they might be able to build it. They've worked a way at trying to make it less expensive to build, and there are certainly a lot of people working on next generation accelerators.
Awesome.
But it is only one of the frontiers.
Mm-hmm.
You have this, what we call the high energy frontier. This has been canonized in a certain sense. We have that. We have the intensity frontier. So where you actually are looking at processes that require very intense or very high rate collisions. You have what we call the precision frontier, where you're trying to make measurements that are increasingly precise, that might actually reveal what's going on. You could discover supersymmetry that way, for example. And you have the cosmic frontier, where you're trying to understand the behavior of the cosmos. This is where we get into dark energy and dark matter. So you have these different frontiers that all are part of particle physics. So the LHC is only one of the frontiers, and arguably a second, because it's also increasing its intensity. So
That's
not
good.
only are you increasing the energy, but you're also increasing intensity. So it kind of sits within those two frontiers. Or
So maximizing all of this, all of these frontiers will be the future, basically. That's where we're headed.
You just
That's
push,
good
you
to,
just
that's
push,
good to know.
push.
Good to know. Good to know.
Yep.
Okay, so we have something to look to. We have something to look forward to. We're not okay.
Exactly.
That's good. That's good.
We're not any dead ends here.
Cool.
We
that's
have
always
a bunch of
nice to
questions.
hear.
Yep. The standard model is alive and well in that it has some problems. We know it's not complete, but it's made predictions. And now we have to sort of understand what in fact is really going on. And okay, that's the ways, we actually talked about, this idea of how science moves forward. And this is, it's what we actually call bread and butter science, actually, at the moment. It's not revolutions, it's bread and butter.
Nice.
Yeah.
Nice.
Awesome.
Cool.
All right.
I think I'm all through, Parker.
Yeah, no, it's been an awesome conversation.
Awesome conversation. Thank you so much.
I learned a lot.
You're welcome.
Thank you.
It's been my pleasure. And, as you can tell, I enjoy these conversations.
Thank
these
you.
Are
I
the
mean,
type
I
of
mean, it looks like, I think we were
conversations.
having quite a lot of fun. We got into some really cool nitty-gritty particle physics stuff. We didn't talk really about dark matter or anything at all this episode.
Not really.
Well, that's okay though. I think particle physics was the main focus, and I think we did get through basically everything we were wondering about. Like, we got some really cool content. So thank you for that. Thank you for coming on for
You're
sure.
welcome.
All right.
You're
As
welcome.
always, go ahead.
Oh, no, I was just going to say, I think this series is great.
Thank you.
Thanks.
And,
Thank you.
I'm really pleased that you've got up to, this is
62. 62. Episode
And,
62.
You have over 10,000, close to 10,000 subscribers. This is awesome.
It's awesome.
So
It's awesome.
just keep it up.
really is.
Just keep it up.
Yeah.
Thank you.
Just keep
Thank
it
you
up.
so much. Thank you.
Awesome.
Thank you.
As always, we'd love to have you on again for, another conversation about possibly a different topic. So yeah. Other than that, I guess we can just end it here. So
Yes, sir.
to everybody listening, make sure to follow the podcast. Make sure to leave a comment. Maybe you want us to talk about something next week. We do answer our emails and all that stuff. You can find us on Instagram at math.physics.podcast. And this has been episode number 62 of the Math and Physics podcast. I'm your host, Parker.
And I'm Ray, and we'll see you soon.
Bye, guys.